Okay, just let's briefly look at this slide here because there were some errors in the original signified by this star. Someone asked what's QTR? Well, Q is the partition function, and all that we're doing here is working out the partition function as a function of the distance between the CH3 and the H. And W is the sum of states. I'm afraid there have been a couple of implementations of this series of talks, and in the set of notes you've got, that's crept through as an N, and that should be a W. So if you could correct that to a W, and this also to a W. So what it's saying is, as we were saying earlier on, the transition state theory is at the position in the minimum in W, or if you're doing it canonically, you're doing it at a particular temperature, it's at the minimum in the partition function. And we're talking over coffee, or just before coffee. One way to think about this is that the transition state, okay, so if you think about this canonically at a particular temperature, then the transition state is at the maximum in delta G. So as we go from the reactants towards the products, then delta G reaches a maximum. And delta G is equal to delta H minus T delta S. And usually, for a constrained transition state, it's the change in the enthalpy, the increase in the enthalpy, that determines where the transition state is. So that's in a situation where you're going like that. And so the maximum, so this is the maximum in delta G, and that gives us the position of the transition state and the value for delta G dagger in the expression for the rate coefficient. But when we're looking at potential energy surfaces that look like this, what's happening is that this is decreasing, but this also is decreasing. So this is leading to a decrease in delta G, this is leading to an increase in delta G, and the transition state occurs where delta G reaches a maximum, mainly because of that entropy term. So delta G dagger, once again, is at the maximum in delta G. So that's looking at it from an entropic point of view. Yeah?
Wouldn't we need to be just a bit more specific? Because one could envision situations in which delta G would be much higher than the transition state. So wouldn't we need to say that it's maximum in delta G along the reaction?
Along the reaction coordinate.
And minimum in delta G along all those coordinates?
Not necessarily. Well, what's going to... Yeah, this is an interesting point. What we've done is we've shown the reaction coordinate along here like that. If we look at if we look, for example, at the symmetric stretching motion in ABC, then that's going to lead. So if we look, imagine this being. So that's coming out of the board. So this is perpendicular. So that's perpendicular to the plane of the board. And so you can think of this as a vibration occurring at the transition state. And as that vibration occurs, then the energy necessarily increases because there's a restoring force. Or the energy increases leading to that restoring force. And so this is the point that's being made, that this point here is actually a saddle point. If you imagine going through a walk through the mountains, then you can imagine going up towards a point in the mountains where you can then begin to go down the other side, but on either side of you, the energy, the altitude is increasing. So you're not at the top of the mountain, you're at a pass. You're at the top of the pass. And this saddle point, or transition state, is really at the top of that pass. And so when you're finding this transition state, it's not an absolute maximum you're finding the minimum in the minimum energy along the reaction coordinate at this particular saddle point. Is that fair? Okay.
So would that mean that if we plot delta G versus the reaction coordinate, we will always get a peak regardless of whether it's a radical reaction or a radical?
Yes, because that's going to determine, yes, but you've got to do it with delta G rather than delta H or delta E. Okay. So for a radical reaction, E itself is not going to give you the transition state. It's going to be delta G that gives it. And generally speaking, it's delta G that gives it, but usually it's dominated by the enthalpy term or the energy term. Yeah. Right. Okay, let's go on and investigate this in a little bit more detail. So what we're going to do is we're going to look at CH3 and H. And we're going to define vibrations as being conserved vibrations or transitional vibrations or modes of motion. And so these are the vibrations in CH3. These are group theory symbols, which you don't need to worry about, except that what they mean is, so there's one vibration, which is a CH stretch at 3004 wave numbers. This E means there are two vibrations there at 3161 wave numbers, so there are three CH stretches corresponding to the three CH bonds. This motion here is a deformation mode where the angles between the CH3s change. CH3 is a planar molecule. And then finally, this vibration here is the umbrella vibration. So we can imagine there's the CH3 plane. It's a planar molecule, and the H's are bending like an umbrella. You're pushing an umbrella in and out. And then these are the vibrations in CH4. So now we've got 4 CH vibrations, and then these at 1534 and 1306 are what are called deformation modes again. So the angles between the CH4s, the CH bonds are changing. Okay, we've been through this. The molecule has 3 degrees of freedom, etc., so I don't need to go through that again. So this is what's happening when CH3 and H come together to form CH4. So we've got 3 translations and 3 translations in CH3 and H, 3 rotations in CH3, 6 vibrations in CH3. In CH4, we've got CH4 dagger. We've got 3 translations. This is the motion of the center of mass of the system. 3 rotations and 8 vibrations plus the reaction coordinate. And what we've got to do is to convert these modes of motion into these modes of motion. So what happens as we go from the reactants into the transition state? Well, 3 translations, the motion of the center of mass is going to convert into the motion of the center of the mass. 2 translations are going to go into 2 rotations. So what you can imagine there is that here's a CH3, here's the H, they're moving along like this, and when they form the transition state, this is going to lead to a rotational motion. Okay, so the 2 are going to be rotating in space. So 2 translations, the one in the plane of the board and the one perpendicular to the plane of the board, are going to lead to rotations. 1 translation is going to lead to the reaction coordinate, so the H is coming into the CH3, and that's going to be the reaction coordinate. two rotations are going to lead to deformation modes. So you can imagine that the CH3 is rotating here, and it's coming in towards the H, and it's getting more and more hindered. And so that's going to go over to a motion in which there's the hydrogen atom, and this CH3 is moving like that or like that. And that motion has come from rotational motion. So rotation is going to go into a deformation vibration. One rotation is going to go into a rotation. I forgot about that on the slide that you've got. So there should be, in addition to all of these, 1R going into 1R. And so that's basically the rotation of the molecule like this, which is going to go into rotation of the molecule as a whole. Of the fragment like that going to rotation of the molecule as a whole. And then we've got the umbrella motion and some deformation modes going into deformation modes, etc. So what I've done is I've starred each of these three types of motion here. So we've got translations going into rotations. And I said that translational energy levels are almost continuous. The spacing between them is very, very small. Rotations, the spacing is wider. Okay? So if we're converting a translation into a rotation, then then the value of W is going to go down. We've got a certain amount of energy available to us. The energy levels are more widely spaced. So W, the number of ways of distributing that energy throughout the molecule, is going to go down necessarily. Another way of looking at it entropically is that we've gone from closely spaced levels to widely spaced levels, and that's going to lead to a decrease in the entropy of the system. Similarly with these others, rotations going into vibrations, rotational levels are more closely spaced than vibrational levels, and these deformation modes, if we go back, you can see that this umbrella motion has got a lower frequency than these deformation modes here, and so it's got more closely spaced energy levels. Okay, so the overall picture of this is that as the molecule forms, the types of motion are becoming more and more constrained. The energy is going down, but the sum of states, but the spacings of the energy levels is going up, and eventually we reach a position where there is a minimum in the sum of states, and that's where the transition state is for that particular energy. And then we can work it out at another energy and find out the position of the transition state there, and which again is determined by the minimum in the sum of states at that energy. Alternatively, we can do it canonically and work at a particular temperature, and we can work out the position of the transition state at that temperature from the maximum in delta G, which is going to be determined by the decreasing enthalpy of the system, but also the decreasing entropy of the system. Okay, so that's CH3 plus H. I've put up the values for CH3 and C2H6, and if you want to have a little exercise, you can look at the correlations in that system. So let's have a look at experiment and theory for these two types of reactions. So this is CH3 plus CH3, and experiments were done using pulse laser photolysis, laser flash photolysis, and photoionization mass spectrometry and absorption spectroscopy. Photoionization spectroscopy at low pressures, absorption spectroscopy at higher pressures. The reaction's second order in CH3, so we need to know the absolute concentration, and this is done either through the absorption cross-section or by correlating the CH3 signal with the loss of acetone, which was the CH3 precursor in these experiments. So what you can do is you can determine a whole series of what are called fall-off curves which we will discuss in more detail in a minute, but we discussed it yesterday. Basically, what's happening is we're coming in, CH3 plus CH3 is coming in and forming C2H6, which is vibrationally excited. It can go back out again, or it can be stabilized. And so as you go to higher and higher pressures, then the rate coefficient increases because this stabilization is getting better and better. And if we look at the rate coefficient versus pressure, it looks something like that. This is K infinity, the high pressure limit, and that's what theory tells us. So theory gives us a value for K infinity, but not directly for the pressure dependence. So what we're wanting to do to compare experiment with theory is to obtain the limiting high pressure value. And that's quite hard. So I won't go through this in any detail because we're going to discuss this in more detail with a better methodology later on. But this is how it was done in 1988 by Wagner and Wardlaw comparing theory with experiment with the experimental data I've just shown you. And so those are their comparisons between theory and experiment. And from those, they were able to get values for K infinity to compare with high-level theories. Now, let's move from 1988 to more recent times. And so these are calculations based on ab initio surfaces of the high-pressure limit. So all we can get from these is what's called the high-pressure limit or the capture rate sometimes. So K infinity depends very sensitively on the potential energy V as the radicals approach. So it's very, very sensitive to the form of this potential energy here. And that's quite hard to do with standard ab initio methods because it depends not only upon the chemical bond being formed, but it also depends upon what are called dispersion forces. If you consider two argon atoms interacting with one another, then dispersion forces arise because of distortions in the electron clouds around the argon atoms, which produce a momentary dipole moment in one atom that induces a sympathetic dipole moment in the other. And that's a standard van der Waals interaction between two argon atoms. That's why argon can be liquefied. And exactly the same sort of thing happens between these methyl radicals. They're quite polarizable, especially because they're radicals. And so that interaction is important at relatively long distances. And then as you go in, you get the chemical interaction occurring between the two unpaired electrons. So to get the long-range potential is quite hard because you've got to include these dispersion forces. And you need high-level theory in order to be able to do that. So this potential depends upon the level of theory used. And so this is a whole series of potential energy functions calculated at different levels of theory. And this is the highest level of theory here. And you can see these are the energies in kilocalories per mole. We're going eventually to form C2H6. So C2H6 is formed way down here. But nevertheless, there are significant differences between these potential energy curves at large distances. And remember just what we talked about in general terms, that decrease in potential energy is very important because it's the interaction between that and these so-called transitional modes, which are changing between the reactants and the products, that leads to the minimum in W. The calculated value for K infinity T varies by more than a factor of 10 as the level of theory is changed. So doing low-level or relatively low-level calculations for a system like this is useless because you're going to be way, way out in the calculation. If provided you use high-level theory, really high-level theory, then the calculated values may in the end, especially at higher temperatures, be better than the theoretical value. The theoretical values may be better than the experimental values, provided you, because with the experimental values, you've got to extrapolate up to the high pressure limit. This is a really moot point. I'll give you a reference at the end where this is discussed in some detail for CH3 plus CH3. That's at the end of the week. So this is an interesting issue about whether theory is actually better or not than experiment. So here's a comparison. So these are this is the highest level of theory here, and this is experiment, and these are obtained by extrapolation to the high pressure limit. So these are using those data I showed you before and extrapolating to the high pressure limit. And these are other theoretical estimates. Remember, this is the high pressure limit as a function of temperature. And one of the interesting things here, and somebody raised this question earlier on, and that is that the rate coefficient decreases as the temperature goes up. Why is that? Well, it's because as you go up in temperature, or as you go up in energy, then the transition state occurs at smaller internuclear separations. And at smaller internuclear separations, the vibrations are much more constrained. So you've converted these transitional modes, which are changing from the reactants to the transition state, you've made them even more constrained than at lower energies. And so that means their entropy is lower than the entropy at lower temperatures or lower energies. And as a result of that, so what that means, I haven't explained that very well. If anybody wants me to go through it, then please ask. But what we're saying is that at these higher temperatures, the transition state is occurring at smaller internuclear separations, and so the system has significantly lower entropy than it has at these lower temperatures up here. Okay, so that's saying that there's reasonably good agreement between experiment and theory, but there are some issues. I also mentioned this business of reflection. So you go through the transition state, and we assume that there is no return. But sometimes, depending upon the nature of the transition state, or the nature of the potential energy surface beyond the transition state, you can get reflections. And so this is what's called a dynamical correction that was introduced to these calculations by Stephen Klippenstein. And so there's the rate coefficient without the dynamical corrections. There's the rate coefficient with the dynamical corrections. And in principle, it looks as if it's giving better agreement with experiment. Over this range up to 500K. These are calculations for CH3 plus C2H5. Here's CH3 plus H. This is a hard experiment to do. One of the best graduate students that I've ever had did these experiments. A guy called Brew Odd, who is now a professor at Oxford. And this is all he did in his PhD, was to measure rate coefficients for CH3 plus H as a function of temperature and pressure. And this was in the middle 80s, and you didn't sort of put things straight in. The numerical methods were not as good in those days as they are now. Computers weren't as good as they are now. And what he had was a single sheet of graph paper sitting on his bench, to which he added the rate coefficients as he went through his 3.5 years of PhD. And this piece of graph paper was covered in vacuum grease, tears, blood, and he really sweated these data out, and it was a great achievement. They're really very hard experiments to do. So what you're doing is it's quite hard to do CH3 plus CH3 because you've got to know the absolute concentration. Here you're looking at two different radicals. So what he did was to produce CH3 by the photolysis of acetone, and the photolysis of acetone also produces a small amount of H, about 1% of the concentration of CH3. So he generated H and CH3 together with H very much less than CH3. And he looked at H by resonance fluorescence, which is rather like laser-induced fluorescence, but older-fashioned and in some ways easier. And CH3 by absorption, because we need the absolute CH3. Since this is supposed to be here, it's not very clear, this is the pseudo-first-order rate coefficient for the reaction of the hydrogen atom is equal to the second-order rate coefficient multiplied by the concentration of CH3. So he needs the absolute CH3 in order to interpret that decay. And so this is the decay of CH3. This is the decay of H. Sorry, that's the wrong way around. That's the decay of CH3. This is the decay of H in the presence of CH3. And you notice that the hydrogen atom decay is highly non-exponential because at long times the CH3 concentration has fallen substantially. And this was the analysis method he used. I won't go into it in any detail, but basically he analyzed the CH3 absorption and got the rate coefficient for CH3 plus CH3. And then he analyzed the hydrogen atom profile, which is somewhat more complicated. And from that, he was able to determine rate coefficients. And so here are the rate coefficients as a function of temperature and pressure. And this is the graph that was sitting on Mark's bench for all those years, covered in all sorts of things. And this has been the only study, the only real study of CH3 plus H under these sorts of conditions. There have been some very high temperature measurements of it, but under these lower temperature conditions, this is the only study. And the key thing here is that we're a long, long way away from the high pressure limit. And it's the high pressure limit that we need in order to compare with theory. So what he did was to look at the reaction between CH3 and D, and this forms a transition state that looks like that, or an energized molecule that looks like that. And this almost exclusively falls apart to give CH2D plus H, because what are called the zero-point energies changes that take place in this system. So this is essentially an exothermic process where you've scrambled the deuterium in there. If you increase the pressure, then you stabilize this, but the main thing is there's nothing going back there because this exothermic process occurs significantly more rapidly than the reverse dissociation. So what you're doing is you're measuring Ka, and Ka is equal to K infinity. So what he was able to do then was to get K infinity using this methodology. So he couldn't get it by extrapolation very easily. He did. I mean, he did. On this next slide, you can see the calculations that he did. but there were very long extrapolations to get there. So here's a comparison between experiment and theory. So these are calculations by Stephen Klippenstein. These are the higher temperature measurements that I referred to, again using this deuterated methodology by Joe Michael. And these are our measurements at lower temperatures using a variety of methods, mainly Mark Brew Odd's methods, but also some experiments done by Paul Seekins. And so there's theory, and interestingly now, the rate coefficient increases as the temperature goes up. And that's because this system is much less constrained. We've got CH3 reacting with a hydrogen atom. It's much less constrained than is the case when you've got two radicals interacting with one another. So these are the experiments that were done by Sue and Michael, so it describes the methodology. Again, they used this CH3 plus D experiment. And these are calculations on H plus alkyl radicals. And these are quite interesting because they show you the constraints that occur as you go to larger and larger radicals. So we've looked at H plus CH3, and the rate coefficient is pretty big. It's of the order of 10 to the minus 10, slightly more than 10 to the minus 10. So there we are, 3, 4 times 10 to the minus 10 up there. There's CH3, and this is the potential surface as a function of angle for a hydrogen atom coming in. And the potential is going to be positive if it comes in from this direction, but it's negative if it comes in from this direction down there. If we go to the H plus ethyl, then these positive potentials, which are going to stop reaction occurring, are much more extensive. And if we go all the way to tertiary butyl, then the angles at which the hydrogen atom can get in and form the molecule are much, much, much smaller. And so the rate coefficients go down as you go from CH3 plus H to tertiary butyl plus H. Sorry.
Are these potential energy surfaces measured or calculated?
These are calculated.
Just through the same theory that...
Yeah.
Okay.
So what you're doing is you're looking at the potential, you're taking the hydrogen atom around the radical and looking at it approaching from different directions. And if it's approaching from one of these methyls, here's a methyl group, if it's approaching from that direction, then it's not going to really be able to access that p orbital that the odd electron is in.
Wouldn't the surface actually be three-dimensional?
Yes, it would. Yeah.
Is there a symmetry plane? That's why you don't need to figure out the other direction?
You do need to figure out the other direction. So this is just a projection in a particular angle. And interestingly, Dave Golden at Stanford has extensively used something called a Gorin model, and the Gorin model is based on the degree of exclusion of approach of say, a hydrogen atom with these radicals, and it's quite a simple but successful theory. Very quickly, one of the things that we've done is we've talked about van der Waals interactions between molecules. These are very important if you have, say, a polar molecule, a ketone, an alcohol, interacting with a hydroxyl radical. And so there are often hydrogen-bonded interactions and certainly polar interactions between the two. And these can give rise to a van der Waals well. And so here we're coming in from long distances out here, and then here's what's called the inner transition state. So in the case of that OH plus dimethyl ether surface I showed you before. Unfortunately, it was going in the opposite direction, but here's OH plus DME here. Here's the van der Waals well, and here's the inner transition state. And it's what, in this case, it's what's called a submerged inner transition state. And so what you can do is you can imagine that there are two possible transition states. The outer transition state, which is rather like the transition states that we discussed here, which are determined by these dispersion forces or by these polar forces, and then an inner transition state, which is here. And again, there was an error in the slide that I gave you. The ends at the bottom of this slide should be W's. And what we do, in order to calculate the rate coefficient, we determine the minimum flux. So under some conditions, this is going to, low temperature conditions especially, this is where the minimum in the flux is going to be. At higher temperatures, this is where the minimum in the flux is going to be. The energy levels are more widely spaced here, but there's more energy available to distribute amongst them. And so what can happen is we can switch from an outer transition state to an inner transition state. And that's a discussion there. And I will simply refer you to this paper here. I'm running out of time, so I will go through this. I will just skip most of this. But for a detailed discussion, if you're interested in these types of transition states, you've got a beautiful discussion in this paper by Greenwald et al. In JPhys Chem from 2005 for the reaction between C2H4 and OH.
For this one as well, the math equals hydrogen radical. What's typically determined as high pressure?
The high pressure limit is around about 3 or 4 times 10 to the minus 10 centimeters cubed per molecule per second. So they're fast. They're really fast. Okay. We've talked about high pressure limits. What I want to do now is to go on and talk about how we deal with pressure dependence. And what we do is we use something called a master equation analysis. And so here what we've got is a simple dissociation or association. So here's AB, and this could be ethane. It could be anything you wanted, which can dissociate to form products. So this could be ethane dissociating to form CH3 plus CH3. And what we do, so if we look at ethane, then it's got many, many energy levels, different ways in which you can distribute the energy amongst the molecules, amongst the various vibrations and rotations of the molecule. Far, far too many to deal with. And so what we do is we bundle them together into grains, what we call grains that maybe have a width of 0.5 kilocalorie per mole or something like that. And we can talk about the number of states within these grains. And then what we do is we set up rate equations for each of these grains. So we treat each of these grains, if you like, as a chemical species. I'll retract that. We set up a rate equation for each of these grains. And so, for example, this grain up here could be formed by energy transfer from lower grains. So here's energy transfer forming this grain here from this lower grain down here. Or it could be deactivated, collisionally deactivated to this lower grain. It could dissociate to form the products, or if we're looking at an association reaction, it could be formed by association. And so we've got a series of chemical and physical processes, chemical reaction and energy transfer. And so what we do is we can write down a rate equation for the population, the concentration of each of these grains. So we express it as a matrix equation, dc by dt, and this M here is a matrix which contains all of these different processes. We'll look at one or two matrices in a little bit more detail. And the time-dependent populations of the grains depend upon the initial concentrations. As with all of these things, it's an initial value problem. What we can do is we can determine the time dependence by looking at the eigenvalues and the eigenvectors of this matrix M. And it turns out that, so the total number of eigenvalues, so eigenvalues, the reciprocal, eigenvalues are all negative for this system, but if we take the magnitude of the eigenvalue and take its reciprocal, then that gives us a time scale for a particular process. And there are as many eigenvalues as there are grains. But the smallest, the eigenvalue of smallest magnitude corresponds to minus the dissociation rate constant if we're looking in this direction, or minus the association rate constant if we're looking in the other direction. So by looking at this eigenvalue spectrum and looking at the eigenvalue of smallest magnitude, we can get the rate constant that we want. And that rate constant is going to depend on pressure because of these collisional processes. And as we increase the pressure, it will eventually go over to the high pressure limit. Okay, here's a bit of algebra, and I apologize. I've changed from C here to rho here. So this is the concentration of a given grain, but it's normalized. So this is the probability of the system being in this particular grain. So there's d rho of E and T. So that's the energy of the grain. That's time. And that depends upon omega, where omega here is the collision frequency, multiplied by the probability on collision of being transferred from the grain at energy E prime to the grain at energy E, multiplied by the probability density of being in the grain at energy E prime. So that's production of this grain by collisional energy transfer from other grains. Here's collisional loss. So this species is taken out of that grain on collisions and transferred to all the other grains. And then this is the rate coefficient for dissociation at this particular energy, which we would calculate using that standard expression W dagger over H NE, multiplied again by the probability density at that grain there. And a key feature of this is this probability of going from one grain to another on collision. And what we do is we use this model here, which is called an exponential down model, which does have some theoretical justification, but is largely empirical. And what it says is the probability of going from energy E prime to E decreases exponentially as the energy gap increases. So you're going to go mainly to energy grains which are quite close together, and the probability of a big jump is quite small. So that's if E prime is bigger than E, and then we can get the probability of going upward energy transfer by what's called detailed balance. So ultimately, these collisions are going to convert the system to a Boltzmann distribution, provided there's no reaction. So they've got to obey a set of rules that would generate a Boltzmann distribution in the end. And we can calculate the upward probability from the downward probability using what's called detail balance and using this need to ultimately generate a Boltzmann distribution. Then we can solve the master equation. This is this matrix M, and out of it we get the eigenvalues. And as I said, the eigenvalue of smallest magnitude is equal to minus the unimolecular rate coefficient for dissociation. If you're interested in this area, there's a beautiful book, which is very old now. Whether you can get it or not, I don't know, but I'm sure libraries stock it, by a man called Hugh Pritchard. And this is a diagram that's taken from his book. And one of the things that I said was the total number of eigenvalues that you get is equal to the total number of grains in your master equation. Okay? And this shows the distribution of those grains as a function of pressure. So as you increase the pressure, the eigenvalues increase. So these are the eigenvalues. So that should be, these are the values of the eigenvalues. These are the magnitudes of the eigenvalues, the logarithm of them. As you increase the pressure, the eigenvalues increase. And there's this bundle of eigenvalues here, which refer to collisional energy transfer. So collisional energy transfer occurs rapidly. And what we're assuming in order to interpret this is that those collisional relaxation eigenvalues are significantly separated from this eigenvalue down here, which is the unimolecular rate coefficient. And as a function of pressure, that shows the standard behavior that we've discussed down here, going up to a limit, which is K infinity. We can, I won't go through this in any detail, but we can also look at association rate coefficients in the same way. So what you can do is you can look through this in some detail. What I'll do is I'd like to talk about one of these. This is an isomerization reaction. So this, we'll talk later on about pentyl radicals. And so this is the probability density for isomer A at energy E. And we're going to get energy transfer within the isomer. So the collisions can't take one isomer over to another isomer. We can only go from one isomer to another by a reactive process. So this is the probability of energy transfer within isomer A. And this is forming this grain at energy E within isomer A. This is removing it. And then this is the loss of isomer A to isomer B, rate coefficient Ka of E, probability density rho A. And this is going from isomer B to isomer A. And that has to occur from a grain with the same energy in isomer B. So what we're doing then these are a couple of isomers, A and B. We've got energy grains like this, and we can have energy transfer within each of these isomers and transfer between the isomers, but that transfer has to be energetically conservative. It can only occur with conservation of energy. So we have, if we're at energy E, we're considering energy E in, for rho A, we've got to go from B at exactly the same energy. And the matrix that we use has an interesting structure. This here corresponds to what's going on within well A. So these are the energy. This is energy transfer from one particular grain to this particular grain here. So the off-diagonal elements here correspond to energy transfer processes into grains, and the diagonal elements correspond to loss of the grain. These are all negative. They correspond to loss from that grain by isomerization and also energy transfer out of that grain. And so here's another one down here, another block for isomer B. And then these off-diagonal blocks here correspond to the transfer from isomer B to isomer A and from isomer A to isomer B in these isoenergetic processes. So that's the structure of this matrix that's used, and it's the eigenvalues and eigenvectors of this matrix that are important in determining the kinetics that we want to find out. Okay, what we'll, let me just check just a second. Okay, I think that's going to be a good place to break. Are there any questions? Have I been less than lucid?
Last I heard you were talking about so you have to take it, you have to do it at the same grain for each isomer. So that's
So the isomerizations have to occur at the same energy. Okay, right. Well, you can. What we'll do afterwards is I'll go through this diagram, but I'll use that as a way of trying to summarize what I've just been talking about. Okay, so don't despair.